In November 2024, a metal tower caught a falling skyscraper out of the sky. That skyscraper was the Super Heavy booster, the first stage of SpaceX's Starship, and it had just returned from the edge of space traveling at supersonic speeds. Two massive mechanical arms, affectionately called chopsticks, closed around the booster's grid fins with millimeter precision, arresting over 5,000 tons of metal that moments before had been plummeting toward the Gulf of Mexico. The crowd at SpaceX's Starbase facility in South Texas erupted. Engineers wept. Elon Musk posted on social media with uncharacteristic restraint, simply saying, "The tower has caught the rocket." This was not just another milestone in spaceflight. This was the moment that changed everything. Because Starship isn't just another rocket. It's not an incremental improvement over what came before. It is the most advanced rocket ever built, and depending on how you measure advancement, it's not even close. Standing 120 meters tall when fully stacked, Starship dwarfs every rocket in history. The Saturn V, which carried humans to the moon, was 111 meters. The Space Shuttle, stacked with its external tank and solid rocket boosters, reached just over 56 meters to the tip of the orbiter. Starship is a behemoth. But size alone doesn't make it advanced. What makes Starship revolutionary is that every single piece of it is designed to come back. The Super Heavy booster, all 70 meters of it with 33 engines, returns to the launch site. The Starship upper stage, 50 meters tall with 6 engines, returns from orbit. Nothing is thrown away. This is full reusability, the holy grail of spaceflight that engineers have pursued since the dawn of the space age. To understand why this matters, we need to talk about money. A Falcon 9 launch, already the cheapest option on the market thanks to booster reusability, costs around $67 million. A United Launch Alliance Atlas V goes for about $110 million. NASA's Space Launch System, the rocket that will supposedly take astronauts back to the moon, costs $4.1 billion per launch. Not a typo. Billion with a B. That's the fully burdened cost including development, ground systems, and operations, spread across the expected number of launches. Now, the Falcon 9 already reuses its first stage, which contains most of the rocket's value. That's why it's so much cheaper than the competition. But the second stage, the part that actually reaches orbit, is still expendable. It burns up in the atmosphere or crashes into the ocean after every flight. With Starship, nothing is lost. SpaceX estimates that once the system is operational and flying frequently, the marginal cost of a Starship launch could drop to as low as $2 million. Let me repeat that. From $4 billion to $2 million. That's a reduction of 3 orders of magnitude, a factor of 2,000. If that seems too good to be true, consider that the Falcon 9's marginal cost, the actual expense of propellant and operations for a single flight on a pre-flown booster, is estimated at around $15 million. Most of a Falcon 9's $67 million price tag is profit margin and amortizing the cost of building new second stages. Starship could genuinely achieve costs in that ballpark because the most expensive part of any rocket is building it in the first place. If you never throw any of it away, you only have to build it once. This is why Starship represents a paradigm shift. It's not just better, it's different. It changes the entire economic equation of spaceflight. But achieving full reusability required solving problems that have stumped aerospace engineers for 70 years. Let's start with the engines. Starship's Super Heavy booster is powered by 33 Raptor engines, 33. For context, the Saturn V's first stage had 5 F-1 engines. The Space Shuttle had 3 main engines plus 2 solid rocket boosters. The Soviet N-1 moon rocket, which never successfully flew, had 30 NK-15 engines on its first stage, and the complexity of managing that many engines simultaneously was part of why it kept exploding. SpaceX is flying 33, and they've made it work. Each Raptor engine produces about 230 tons of thrust at sea level. Multiply that by 33, and you get roughly 16.5 million pounds of thrust at liftoff. That's more than the Saturn V's 7.6 million pounds. It's more than the SLS's 8.8 million pounds. Starship generates nearly twice the thrust of the rocket that took humanity to the moon. But the Raptor engine's real advancement isn't thrust, it's efficiency. The Raptor uses something called a full-flow staged combustion cycle. Now, most rocket engines work by burning fuel and oxidizer in a combustion chamber, which produces hot gas that shoots out a nozzle, creating thrust. Simple enough. But you need to get that fuel and oxidizer into the combustion chamber at extremely high pressure, and that requires pumps. Powerful pumps. In most rocket engines, you drive those pumps by burning a small amount of propellant in a preburner, using that hot gas to spin a turbine connected to the pump. Then you dump that preburner exhaust somewhere. In an open-cycle engine, you just throw it overboard. Wasteful, but simple. In a closed-cycle engine, you route it into the main combustion chamber, which is more efficient but more complex. The Space Shuttle's RS-25 engines used a staged combustion cycle where the fuel-rich pre-burner exhaust went into the main chamber. Very efficient. The problem is that you're still only running one pre-burner, which means you're only pre-burning one of your propellants. The Raptor uses full-flow staged combustion, which means it has 2 pre-burners. One burns fuel-rich, driving the fuel pump. One burns oxidizer-rich, driving the oxidizer pump. Then, both exhaust streams meet in the main combustion chamber, where they burn together completely. This is monstrously difficult to engineer because you're running oxidizer-rich combustion, which means hot oxygen is flowing through your turbomachinery, and hot oxygen is spectacularly good at setting things on fire, including the metal components of your engine. You need exotic alloys, precise cooling, and manufacturing tolerances measured in micrometers. Only 2 full-flow staged combustion engines have ever flown. The Soviet RD-0270, which never made it past testing, and the Raptor. SpaceX is now building roughly 1 Raptor engine per day at their facility in Hawthorne, California. The performance benefits are substantial. The Raptor achieves a specific impulse, a measure of efficiency, of around 330 seconds at sea level and 380 seconds in vacuum. For comparison, the Merlin engines on Falcon 9 get about 280 seconds at sea level. Higher specific impulse means you get more thrust per kilogram of propellant burned, which means you can carry more payload or have more margin for recovery. Then there's the fuel choice. The Raptor burns liquid methane and liquid oxygen. Most rockets use either RP-1, which is basically kerosene, or liquid hydrogen. SpaceX chose methane for several reasons. First, it's dense enough to keep tank sizes reasonable, unlike hydrogen, which has terrible density and requires enormous tanks. Second, it burns cleaner than kerosene, which means less coking, the buildup of carbon deposits in the engine that makes reusability harder. Third, and this is the kicker, you can make methane on Mars. Mars has carbon dioxide in its atmosphere and water ice in its soil. Run those through a Sabatier reactor, and you get methane and oxygen. This is called in situ resource utilization, making propellant from local materials, and it's essential for any realistic Mars architecture. If you had to bring all your return propellant from Earth, the mass ratios would be absurd. With methane, you can fly to Mars, make more fuel, and fly back. The Raptor's fuel choice isn't just about performance on Earth, it's about making Mars missions possible. Now, let's talk about the catch. When SpaceX first started landing Falcon 9 boosters, they used landing legs. 4 legs would deploy, and the booster would touch down on a concrete pad or an autonomous drone ship in the ocean. This worked, and it was revolutionary, but it had problems. Landing legs are heavy. They add dry mass to the booster, which reduces payload capacity. They also require refurbishment between flights. But the biggest problem is that once the booster lands, you have to transport it back to the launch site. If it lands on a drone ship, you have to sail it back to port, load it onto a transport, and truck it to the pad. This takes time and costs money. Starship solves this with the most audacious engineering solution in modern aerospace. Instead of landing legs, the Super Heavy booster returns directly to the launch site, and the launch tower catches it out of the air. The tower, officially called the Orbital Launch Mount but universally known as Mechazilla, has 2 massive arms that swing out to catch the booster as it descends. The booster has hard points on its exterior called catch pins that slot into the arms. When the booster is caught, it's already back at the launch site, suspended in the exact position needed to be restacked on top of a new Starship upper stage. No legs, no transport, no delay. In theory, you could catch a booster, stack a new ship on top, and launch again within an hour. The engineering required to make this work is staggering. The booster is descending at hundreds of meters per second. It has to execute a series of engine burns to slow down, flip itself vertical, and position itself between the tower arms with a precision measured in centimeters. The tower has to track the booster's position in real time and command the arms to close at exactly the right moment. Too early and you miss. Too late and 5,000 tons of metal impacts the ground at terminal velocity. When SpaceX first announced this plan, most of the aerospace industry thought they were insane. Catching a rocket out of the sky with a tower? It sounded like science fiction. And then, on October 13, 2024, during the 5th integrated flight test, they did it. The booster returned from space, threaded itself between the tower arms, and the arms closed with a gentle clang that was picked up by microphones at the launch site. The booster hung there, suspended, still smoking from re-entry, and SpaceX had just obsoleted every other approach to booster recovery. This is what advanced means. It's not just better performance. It's solving problems in ways that redefine what's possible. But Starship's advancement isn't just in its engineering. It's in SpaceX's entire approach to development, and that approach has involved a lot of explosions. The first integrated flight test of Starship, IFT-1, launched on April 20, 2023. The rocket lifted off from Starbase, all 33 Raptor engines igniting in a spectacle of flame and sound that was captured by cameras around the world. For about 10 seconds, everything looked perfect. Then, things started going wrong. Multiple engines on the Super Heavy booster shut down. The rocket began to tumble. It was supposed to separate, with the booster returning to land and the upper stage continuing to orbit. Instead, the 2 stages remained connected, spinning end over end. 4 minutes after liftoff, SpaceX activated the flight termination system. The rocket exploded in a fireball over the Gulf of Mexico. The explosion was the least of the problems. During liftoff, the force of 33 Raptor engines firing simultaneously had obliterated the concrete launch pad. Chunks of concrete, some weighing hundreds of kilograms, were hurled thousands of meters in every direction. The shock wave shattered windows in Port Isabel, 10 kilometers away. A cloud of dust and debris rained down on surrounding areas, including a state park and protected wildlife habitat. The Federal Aviation Administration grounded Starship pending an investigation. Environmental groups filed lawsuits. The media had a field day. SpaceX had just blown up the largest rocket ever built and destroyed its own launch pad in the process. But here's where SpaceX's philosophy diverges from traditional aerospace. Most companies would have spent years analyzing the failure, running simulations, building test articles. SpaceX spent 6 months rebuilding the pad and preparing for the next flight. The launch pad problem was obvious. 33 engines produce an insane amount of force, and concrete, even reinforced concrete, can't handle it. SpaceX's solution was a deluge system. They installed a massive water suppression system under the launch pad that pumps thousands of gallons of water per second onto a steel plate directly beneath the rocket during ignition. The water absorbs the acoustic energy and cools the steel, preventing it from being destroyed. They also reinforced the pad structure and improved the flame trench design. All of this was done in 6 months. For context, NASA has been developing the mobile launcher for the SLS rocket since 2010. It's still not fully operational. SpaceX identified a problem, engineered a solution, built it, and moved on, all while the regulatory process ground along at its usual glacial pace. IFT-2 launched on November 18, 2023. This time, all 33 engines ignited successfully. The rocket cleared the tower, began its pitch maneuver, and after 2 minutes and 49 seconds, executed hot staging. Hot staging is when you ignite the upper stage engines while still attached to the booster, using the exhaust to push the stages apart. It's more efficient than traditional staging, but harder to execute because you're essentially lighting a blowtorch pointed at your booster. The Starship upper stage separated and continued toward space. The Super Heavy booster began its flip maneuver to return. Then it exploded. Telemetry suggests a propellant leak led to an overpressure event that triggered the automated flight termination system. Meanwhile, the upper stage continued climbing. It reached space, flying for several minutes before it too was lost, apparently due to a leak in the oxidizer system. 2 vehicles lost, but unlike IFT-1, this was progress. Staging had worked. The upper stage had reached space. SpaceX had demonstrated that the fundamental architecture was sound. IFT-3 launched on March 14, 2024. This time, both stages performed well. The ship reached orbital velocity and began coasting. For the first time, SpaceX opened the payload bay door in space, testing the mechanism that would be used to deploy Starlink satellites. They also tested propellant transfer operations, moving liquid oxygen between tanks, a critical technology for the orbital refueling architecture needed for Moon and Mars missions. Re-entry was the test. Starship had never survived re-entry before. As the ship hit the atmosphere over the Indian Ocean, cameras mounted on the vehicle showed plasma beginning to form around the nose cone and flaps. The heat shield, made of thousands of hexagonal ceramic tiles, began doing its job. For a while, everything looked good. Then the camera feed cut out. When it came back, the ship was tumbling. It broke apart at an altitude of around 65 kilometers. But SpaceX had gotten re-entry data. They'd seen where the heat shield failed, which tiles came off, how the flaps performed. That data was worth more than the vehicle. IFT-4, launched June 6, 2024, was where things got serious. The booster executed its flip and boost back burn, then performed a landing burn over the Gulf of Mexico. It didn't attempt a tower catch, that was still too risky, but it demonstrated a controlled descent and soft splashdown. Cameras on offshore vessels captured the booster gently touching down in the water before tipping over. Meanwhile, the upper stage survived re-entry. Barely. Camera feeds showed one of the forward flaps burning, its outer layer ablating away as superheated plasma ate through the structure. The flap continued to function even as it glowed white-hot. The ship made it to the planned splashdown point in the Indian Ocean and executed a perfect flip maneuver, transitioning from belly down to vertical in the final seconds before impact. It hit the water intact, then exploded as seawater contacted the hot engines. But it had survived re-entry. SpaceX had proven the heat shield concept worked even if it needed refinement. 5 months later, IFT-5 wrote itself into history with the tower catch. The booster returned to the launch site, positioned itself between the arms, and was caught. The upper stage again survived re-entry and splashed down precisely on target. For the first time, both vehicles had completed their missions successfully. Starship had arrived. This iterative approach, this willingness to blow things up and learn from failure, is alien to traditional aerospace. When NASA designs a rocket, they spend years in analysis. They build test articles. They run thousands of simulations. They test every component to destruction in ground facilities. Only after all of that do they attempt a flight, and that flight is expected to succeed because failure is unacceptable. The SLS program has cost $23 billion over 12 years and has flown twice. Starship has flown 6 times in 20 months and cost a fraction of that. SpaceX's approach is summed up in a phrase you hear constantly at the company: hardware-rich development. Build lots of rockets, fly them, break them, learn, build better rockets. It's faster and, counterintuitively, cheaper than the traditional approach. Each Starship costs roughly $100 million to build, maybe less now that production has ramped up. That's expensive, but it's not astronomical. The SLS core stage alone costs about $590 million. SpaceX can afford to blow up a few Starships to learn what works. NASA can't afford to blow up a single SLS. This philosophy extends to every aspect of Starship's design. Take the heat shield. Traditional heat shields, like the ones on Apollo or the Space Shuttle, were carefully engineered, extensively tested, and precisely manufactured. Every tile on the Space Shuttle had to be individually shaped and fitted. It took an army of technicians to inspect and maintain them between flights. Starship's heat shield is 18,000 hexagonal tiles that are far simpler. They're not custom-fitted. They're attached with pins and clips, not adhesive. And SpaceX expects some of them to fall off. In fact, tiles fell off during every re-entry until IFT-5. But the ship survived anyway because the heat shield has redundancy built in. Losing a few tiles isn't catastrophic. This design philosophy, accepting minor failures as acceptable rather than engineering them away completely, is part of what makes rapid iteration possible. And it drives traditional aerospace engineers absolutely mad. The explosions weren't accidents. They were data collection events that happened to involve disassembling rockets at high velocity. This distinction matters because it reveals something fundamental about how SpaceX approaches the problem of building the world's most advanced rocket. When IFT-1 lifted off on April 20th, 2023, SpaceX knew there was a non-zero chance the launch pad would be destroyed. They knew it, and they launched anyway. The question you might be asking is, why? Why not test the pad first? Why not build a flame diverter before the first launch? The answer is that SpaceX needed to know exactly how much force 33 Raptor engines would exert on the pad under actual flight conditions, with a real vehicle, real propellant flow rates, and real aerodynamic effects. You can model this, you can simulate it, but simulation has limits, especially when you're doing something that's never been done before. The forces involved when 33 engines ignite simultaneously, each producing 230 tons of thrust, are difficult to predict with perfect accuracy. Acoustic waves reflect off surfaces in complex ways. Supersonic exhaust plumes interact with the ground, with each other, with the atmosphere. You can get close with computational fluid dynamics, but close isn't good enough when the difference between close and accurate is whether your launch pad survives. So SpaceX launched, knowing the pad might be destroyed because destroying the pad would tell them exactly what they needed to build. And it did. The concrete didn't just crack, it exploded. Chunks of it were found kilometers away. The launch mount itself survived mostly, but the pad surface was gone. The flame trench, designed to channel exhaust away from the rocket, had been overwhelmed. Within hours of the explosion, SpaceX engineers were on site surveying the damage. Within days, they had a plan. Within weeks, construction began. The solution was the water deluge system, but implementing it was not trivial. The system pumps an enormous volume of water, sourced from holding tanks built specifically for this purpose, through a distribution system under the launch pad. During ignition, water floods onto a massive steel plate directly beneath the rocket. The water absorbs acoustic energy, reduces temperature, and creates a protective barrier between the exhaust and the pad infrastructure. Similar systems exist at other launch sites. Kennedy Space Center's Pad 39A has one for Falcon Heavy, but the scale required for Starship was unprecedented. They also installed a steel plate several inches thick to replace the concrete surface, because steel, unlike concrete, doesn't fragment under stress, it deforms. If the forces are too great, the steel will warp or melt, but it won't turn into projectiles. 6 months after IFT-1, the pad was rebuilt. Not repaired, rebuilt, with significant improvements over the original design. This is the SpaceX approach distilled: launch, break, learn, fix, launch again. But the pad wasn't the only thing that needed fixing. IFT-1 had demonstrated that the Starship architecture had fundamental issues beyond ground infrastructure. Multiple engines had failed during ascent. The stage separation system hadn't worked. The vehicle had tumbled out of control. Each of these failures provided data, and each required solutions. The engine failures were traced to propellant flow issues and combustion instabilities that only manifested under the extreme conditions of flight. Ground testing is valuable, but it can't perfectly replicate the thermal, pressure, and vibration environment of a rocket accelerating through the atmosphere. Some problems only appear when you light 33 engines under a 5,000-ton rocket and let it fly. SpaceX made modifications to the propellant feed system, improved engine-out capability, so the vehicle could continue flying even with several engines offline, and refined the ignition sequence. The stage separation failure was more complex. Starship uses hot staging, where the upper stage engines ignite while still attached to the booster. This technique, borrowed from Soviet rocket designs, is more efficient than cold staging because you're using the upper stage thrust to push away from the booster rather than relying solely on separation mechanisms. But it also means you're directing 6 Raptor engines worth of exhaust directly at your booster. IFT-1 wasn't supposed to attempt hot staging. It was supposed to use a more traditional separation system, but that system failed to activate. When SpaceX analyzed the data, they realized hot staging was actually a better approach if they could make it work. So they committed to it fully for IFT-2. This required adding a vented interstage, essentially a protective skirt on top of the booster, with holes that allow the upper stage exhaust to escape without destroying the booster. They also reinforced the top of the booster to handle the thermal and mechanical loads. IFT-2 launched 7 months after IFT-1. 7 months from explosion to the next flight. For context, after the Space Shuttle Challenger disaster in 1986, it took 32 months before the next shuttle flew. After Columbia in 2003, it took 29 months. Now, those were crewed vehicles, and the circumstances were different, but the timescale comparison is stark. SpaceX isn't just iterating faster than traditional aerospace, they're iterating on a completely different timescale. When IFT-2 lifted off, the improvements were immediately visible. All 33 engines ignited cleanly. The rocket climbed smoothly. At 2 minutes and 49 seconds, hot staging occurred. The 6 Raptor engines on the upper stage lit while still attached to the booster, and the 2 stages separated. It worked perfectly. The upper stage continued toward orbit while the booster began its return journey. Then, about 3.5 minutes into flight, the booster exploded. Telemetry indicated a rapid loss of pressure in the liquid oxygen tank, suggesting a leak. The exact cause remains unclear, but the leading theory is that hot staging, while successful, caused more damage to the booster than expected, and that damage led to a structural failure during the flip maneuver. The flight termination system activated automatically. Meanwhile, the upper stage was having its own problems. It reached space, becoming the first Starship to do so, but about 8 minutes into the flight, it too experienced an anomaly. The automated flight termination system triggered, and the vehicle was lost. Again, telemetry suggested a propellant leak, this time in the liquid oxygen system of the upper stage. 2 vehicles lost, but the mission had accomplished several critical objectives. Hot staging had worked. The upper stage had reached space. SpaceX had data on how both vehicles performed under real flight conditions, including how they failed. Each failure mode was studied, root causes identified, and design changes implemented. For IFT-3, SpaceX added reinforcement to the areas of the booster damaged during hot staging. They improved the pressurization system to prevent the kind of leak that caused the booster explosion. They redesigned components of the upper stage to address the oxidizer leak, and they added new test objectives because each flight wasn't just about reaching orbit, it was about testing specific technologies needed for the operational system. IFT-3 launched on March 14, 2024. This time, both vehicles performed nominally through staging. The booster executed its flip maneuver and began the coast back toward the Gulf of Mexico. It was supposed to perform a landing burn and soft splashdown, demonstrating the ability to control descent. Instead, it broke up during re-entry. The exact cause was unclear, but video showed the booster starting to tumble before it disintegrated. Likely, residual damage from hot staging or aerodynamic forces during the flip exceeded structural limits. But the upper stage was the real story of IFT-3. It reached orbit successfully. For the first time, Starship was in space, coasting at orbital velocity. SpaceX used this opportunity to test several technologies. They opened the payload bay door, the large clamshell door that would be used to deploy Starlink satellites. Video from the vehicle showed the door opening smoothly, Earth visible through the gap, stars beyond. They tested propellant transfer, moving liquid oxygen from one header tank to another. This was a small-scale demonstration of the technology that would eventually enable orbital refueling, where one Starship would transfer propellant to another in orbit, a capability essential for Moon and Mars missions. Then came re-entry. As the ship hit the atmosphere over the Indian Ocean, cameras showed the expected plasma formation. The hexagonal heat shield tiles began glowing as they absorbed thermal energy. Everything looked nominal. Then, tiles started coming off. You could see them in the camera feed, bright streaks as they separated from the vehicle and burned up. The heat shield was failing, not catastrophically, but significantly. At an altitude of about 65 kilometers, the vehicle lost control and broke apart. It was a failure, but an informative one. SpaceX learned exactly where the heat shield was weakest, which tiles were most likely to separate, and how the vehicle behaved as it began to lose structural integrity. That data informed the redesign of the heat shield for IFT-4. They improved the tile attachment mechanism, added reinforcement in high-stress areas, and modified the tile composition to handle thermal cycling better. They also added additional sensors to monitor tile performance in real time during future flights. IFT-4 launched on June 6, 2024, and it was the first flight where everything mostly worked. The booster performed flawlessly through staging, executed its flip and boost-back burn, and descended toward the Gulf of Mexico. The landing burn ignited on schedule, and the booster performed a soft splashdown, touching down gently in the water before tipping over. It wasn't a landing, exactly, since there was nothing to land on and the tower catch system wasn't ready. But it demonstrated that the booster could control its descent all the way to the surface. That alone would have made IFT-4 a success, but the upper stage was even more impressive. It reached orbit, coasted, and began re-entry. As it hit the atmosphere, the heat shield performed better than on IFT-3. Fewer tiles came off. The vehicle maintained control through the peak heating phase. But then one of the forward flaps started burning. These flaps, 4 of them positioned around the nose of the vehicle, are used to control the ship's orientation during re-entry. They're essentially giant control surfaces that stick out into the plasma stream. During IFT-4, cameras showed one of the flaps beginning to glow. The outer layer, a layer of heat-resistant material, started ablating, burning away as designed to carry heat away from the underlying structure. But the heating was more intense than expected. The flap continued to burn, glowing white-hot, pieces of it visibly disintegrating. Engineers watching the feed assumed the flap would fail and the vehicle would tumble. But it didn't. The flap kept working even as it burned. The actuators, the mechanisms that move the flap, continued to function. The ship maintained control. It descended through the atmosphere, still oriented correctly, still following its trajectory. At an altitude of a few kilometers, it executed the flip maneuver, transitioning from horizontal to vertical. The engines ignited for the landing burn. The ship descended vertically toward the ocean surface, slowing, and then gently splashed down. It remained upright for a few seconds before tipping over and exploding as seawater reached the hot engines. But it had survived re-entry. A controlled re-entry all the way to the surface, with a partially destroyed control surface. The engineering margin built into Starship had been tested in the most extreme way possible, and it had held. This was a revelation. It demonstrated that the vehicle could tolerate significant damage and still complete its mission. The heat shield didn't have to be perfect. The flaps didn't have to be pristine. The system had redundancy and robustness that allowed it to absorb failures without catastrophic consequences. After IFT-4, SpaceX made further improvements to the flap design, adding additional thermal protection and repositioning them slightly to reduce exposure to the most intense heating. They also upgraded the heat shield tiles based on data from all 4 flights. Some areas needed thicker tiles, some needed different attachment methods. Some needed different materials entirely, and they prepared for the most ambitious test yet, the tower catch. The idea of catching the booster with the launch tower had been part of the Starship concept from early on, but implementing it was terrifyingly complex. The booster had to return to the launch site, which required more propellant reserved for the return burn, which reduced payload capacity but eliminated the need for landing legs. It had to position itself between 2 massive mechanical arms with enough precision that the catch pins on the booster exterior aligned with the arms. The margin for error was measured in centimeters. If the booster was off by more than a few dozen centimeters, it would miss the arms entirely and crash into the tower or the ground. The tower arms, officially called the chopsticks because of their appearance, are massive steel structures that weigh hundreds of tons. They are moved by powerful actuators that can position them precisely and close them quickly. During a catch attempt, the arms start in the open position. As the booster descends, the arms track its position. When the booster is at the correct height and position, the arms close and the catch pins slot into place. The booster's weight is transferred to the arms, which are themselves supported by the tower structure. This all happens while the booster is still descending at several meters per second. The timing has to be perfect. Close the arms too early and the booster hasn't reached the right position. Close them too late and the booster has already passed through. The control system has to account for the booster's velocity, its position, wind conditions, and the dynamics of the arms themselves. It's a problem in real-time trajectory optimization and control that pushes the boundaries of what's possible with current technology. IFT-5 launched on October 13, 2024. The mission profile was similar to IFT-4. Reach orbit, test the upper stage, attempt re-entry and splashdown. But this time, the booster would attempt to return to the launch site and be caught by the tower. As the booster separated and began its return, cameras tracked it arcing back toward Starbase. It executed the flip maneuver, transitioning from horizontal to vertical. The boost-back burn fired, pushing it toward the launch site. As it descended, you could see the tower in the distance, the 2 arms open and waiting. The booster dropped lower, engines firing to control its descent. It was coming in fast, still supersonic, a column of flame beneath it. Then the engines throttled back and it slowed. It descended past the top of the tower, still dropping. The arms began to close. For a moment, it looked like it wouldn't work, like the timing was off. Then, with a sound that was captured by microphones as a deep metallic clang, the arms closed around the booster. The catch pins slotted into place. The booster hung there, suspended 70 meters in the air, engines still glowing from the landing burn. The crowd at Starbase went absolutely insane. People were screaming, crying, hugging each other. This wasn't just another milestone. It was a moment that fundamentally changed what's possible in spaceflight. No rocket in history had ever returned to its launch site and been caught out of the air. And SpaceX had just done it on their first attempt. Well, first attempt at the actual catch. They'd been working toward this for years, testing the tower mechanisms, refining the flight software, practicing the maneuvers. But still, first try. Meanwhile, the upper stage completed its mission. It reached orbit, coasted, re-entered, and splashed down precisely on target in the Indian Ocean. Both vehicles had completed their missions successfully. For the first time, a Starship flight had been a complete success. The pace of iteration that led to this moment is hard to overstate. From the first flight to the first successful catch, 18 months, 5 flights, each one building on the lessons of the previous one. Each one testing new capabilities, each one accepting risk in service of learning faster. Compare this to the development timeline of other rockets. The Space Launch System began development in 2010. Its first flight was in 2022. 12 years. It has flown twice. The entire program has cost over $23 billion. Starship has flown 6 times in less than 2 years and cost perhaps $2 to $3 billion total, including all the vehicles, the launch site, the tower, everything. The cost per flight is difficult to calculate precisely because SpaceX doesn't publish detailed financials, but estimates suggest each Starship vehicle costs roughly $100 million to build, maybe less now that production has scaled up. Each booster costs roughly the same, so each flight consumes about $200 million in hardware, plus operational costs. For 6 flights, that's maybe $1.5 billion in hardware, plus infrastructure and operations. Compare that to a single SLS launch at $4.1 billion. SpaceX has conducted 6 test flights of the most advanced rocket ever built for less than the cost of one operational flight of NASA's rocket. This is the power of the iterative approach. Build, fly, break, learn, repeat. Each explosion is expensive, yes, but it's far less expensive than spending years in analysis paralysis, and each explosion teaches you things you couldn't learn any other way. The data from IFT-1's launch pad destruction led directly to the deluge system. The data from IFT-2's booster explosion led to reinforcements that allowed IFT-3's booster to survive staging. The data from IFT-3's re-entry breakup led to the heat shield improvements that allowed IFT-4 to survive. The data from IFT-4's burning flap led to the thermal protection upgrades for IFT-5. Each failure was a stepping stone to success, but this approach only works if you can afford to fail. If each vehicle costs $4 billion, you can't blow up 6 of them to learn what works. You have to get it right the first time, which means spending years and billions on development before you ever light an engine in flight. SpaceX inverted this model. They made the vehicles cheap enough that they could afford to blow them up. The Raptor engine is a perfect example. Traditional rocket engines are precision instruments, hand-built by highly skilled technicians, with costs measured in millions of dollars per engine. The RS-25 engines on the Space Shuttle cost approximately $46 million each. The SLS uses 4 of them per flight, all refurbished shuttle engines, because building new ones is prohibitively expensive. SpaceX designed the Raptor for mass production. It's manufactured using techniques borrowed from the automotive industry. Extensive automation, modular components, high-volume production. The goal is to produce 1 Raptor per day at a cost of around $1 million per engine. Maybe less. They're not quite at 1 per day yet, but they're close. This changes the economics completely. If engines are cheap, you can afford to test them to destruction. You can afford to fly engines that haven't been exhaustively validated on the ground. You can iterate on the design rapidly because the cost of failure is manageable. This is hardware-rich development, and it's not just faster than the traditional approach, it produces better results. When you fly frequently, you encounter real-world conditions that no amount of ground testing can replicate. You discover failure modes you didn't anticipate. You learn what actually matters and what doesn't. The same philosophy extends to the entire vehicle. Starship is built from stainless steel, which is unusual for a rocket. Most modern rockets use aluminum-lithium alloys or carbon fiber composites, materials that are lighter than steel and very strong. Elon Musk initially planned for Starship to be built from carbon fiber. SpaceX even built a large carbon fiber tank and tested it. Then Musk changed his mind and switched to stainless steel. The decision shocked the aerospace industry. Steel is heavy, it's old-fashioned. But Musk had run the numbers and realized steel had advantages that outweighed the mass penalty. First, steel is cheap. Carbon fiber costs hundreds of dollars per kilogram. High-grade stainless steel costs a few dollars per kilogram. When you're building a rocket that's 50 meters tall and 9 meters in diameter, material costs matter. Second, steel is strong at cryogenic temperatures. Most materials become brittle when cooled to the temperature of liquid methane and liquid oxygen, which are stored at around negative 160 degrees Celsius. Steel gets stronger as it gets colder. This means the tanks can be thinner, which reduces mass and partially offsets steel's density disadvantage. Third, steel is strong at high temperatures. During re-entry, parts of the vehicle experience temperatures exceeding 1,000 degrees Celsius. Aluminum and carbon fiber lose strength at high temperatures. Steel remains strong up to around 800 degrees, and even beyond that, it degrades gracefully rather than failing catastrophically. This allows SpaceX to use the steel structure itself as part of the heat management system. Fourth, steel is easy to work with. It can be welded with conventional equipment. It doesn't require autoclaves or clean rooms. You can build with it quickly, and if you make a mistake, you can cut out the bad section and weld in a replacement. Carbon fiber, once cured, is essentially permanent. The switch to steel enabled SpaceX to build Starships quickly and cheaply, which enabled rapid iteration. If each vehicle took 2 years to build like an SLS core stage, they couldn't fly every few months. The production rate supports the test cadence. This is a system optimized for learning, and the results speak for themselves. The heat shield tiles are hexagons, roughly 15 centimeters across, made from a silica-based ceramic material that can withstand temperatures exceeding 1,500 degrees Celsius. There are about 18,000 of them covering the windward side of Starship, the side that faces into the plasma stream during re-entry. Each tile is attached to the vehicle's stainless steel skin with metal pins and clips, a system designed for rapid replacement. If a tile is damaged, you don't need to carefully bond a new one in place like with the Space Shuttle's tiles. You just pop the old one off and clip a new one on, in theory. In practice, keeping 18,000 tiles attached to a vehicle that's experiencing massive aerodynamic forces, extreme thermal gradients, and violent vibrations has proven challenging. During IFT-3, dozens of tiles came off. You could see them in the camera feed, bright streaks as they separated and burned up. During IFT-4, fewer came off, but one of the forward flaps still burned through. By IFT-5, the heat shield performance had improved dramatically, with only a handful of tiles lost. Each iteration revealed which tiles were most vulnerable and why. Some areas experience more heating than others. Some areas experience more mechanical stress. Some tiles are exposed to acoustic loads during launch that weaken their attachment. SpaceX has been systematically addressing these issues, improving the attachment mechanism, adding secondary retention, and varying the tile thickness based on the heating profile. But here's the thing about the heat shield. It doesn't have to be perfect. This is a departure from traditional spacecraft design philosophy, where every tile is critical, and the loss of a few can be catastrophic. The Space Shuttle Columbia disaster in 2003 was caused by a single damaged tile on the wing leading edge. Superheated gas entered through the breach, melting the wing structure from the inside, and the vehicle disintegrated during re-entry. Starship is designed differently. The steel structure can tolerate significantly more heating than the aluminum structure of the shuttle. If some tiles are lost, the steel beneath them will heat up, potentially glowing red-hot, but it won't immediately fail. There's thermal mass and structural margin built in. The vehicle can survive with a degraded heat shield as long as the damage isn't too extensive. This is intentional. SpaceX is designing for resilience rather than perfection. A system that degrades gracefully is more robust than one that fails catastrophically. And it's cheaper to operate because you don't need to inspect and replace every tile after every flight. Only the ones that are actually damaged. The forward flaps are another example of this design philosophy. These are the 4 large control surfaces near the nose of the vehicle, 2 on the windward side and 2 on the leeward side. They're used during re-entry to control the ship's orientation as it falls through the atmosphere belly first. The flaps are exposed to extreme conditions. They stick out into the plasma stream, experiencing temperatures that would vaporize most materials. During IFT-4, one of the windward flaps partially burned through, yet continued to function. For IFT-5, SpaceX moved the windward flaps slightly toward the leeward side, reducing their exposure to the most intense heating. They also added additional thermal protection layers. These changes were based directly on data from the previous flight. The flap burned, therefore we know exactly how much margin we have, therefore we know exactly how much improvement we need. This is test-driven development applied to rocket engineering. But the most complex thermal challenge isn't the heat shield or the flaps, it's the engine bay. The base of Starship, where the 6 Raptor engines are mounted, has to survive 2 extremely different thermal environments. During launch, the engines are firing, producing exhaust temperatures of over 3,000 degrees Celsius. The base of the vehicle is exposed to this exhaust, reflected acoustic energy, and the thermal radiation from the engines themselves. Then, during re-entry, the base is on the leeward side, shielded from the plasma stream by the vehicle's body. But it's not completely protected. Hot gas can flow around the sides and into the engine bay. And when the vehicle flips for landing, pointing the engines downward, the base briefly becomes the leading edge, exposed to aerodynamic heating. Managing all of this requires a combination of thermal protection materials, active cooling, and clever design. The engine bay has heat-resistant tiles, but they're different from the ones on the windward side. They're designed to handle the acoustic and thermal environment of engine operation, not the sustained heating of re-entry. There's also active cooling, where propellant is circulated through channels to absorb heat. And there's geometric design, the way the engines are mounted, the shape of the base, the positioning of the heat shield. All of these affect how heat flows through the structure. Getting this right has required multiple iterations. Early versions of Starship had different engine bay designs that proved inadequate. Tiles came off. Structures overheated. Each problem was identified through testing and fixed in the next version. By IFT-5, the engine bay was surviving both launch and re-entry, though SpaceX continues to refine the design. Another major technological challenge is propellant management in space. On Earth, gravity pulls propellant to the bottom of the tank, where the pumps can draw it in. In orbit, there's no gravity, or more precisely, everything is in free fall, so propellant floats around inside the tank. If you try to start an engine, you might draw in vapor instead of liquid, which would cause the engine to fail or explode. Starship solves this with header tanks and ullage burns. The header tanks are small separate tanks located in the nose and base of the vehicle, designed to keep propellant settled even in microgravity. They're essentially pressurized bottles that ensure there's always liquid at the outlet. When it's time to start the engines for a deorbit burn or landing burn, the vehicle first performs a small ullage burn with thrusters to create a tiny amount of acceleration, settling the propellant toward the engines. Then the main engines can start safely, but this only works for the vehicle's own propellant. For the orbital refueling architecture that Starship requires, you need to transfer propellant between two vehicles in orbit, and that's vastly more complicated. Imagine two starships docked nose-to-nose in orbit. One is the tanker, full of the propellant. One is the mission vehicle, nearly empty, that needs to be refueled. You need to transfer hundreds of tons of liquid methane and liquid oxygen from one vehicle to the other. In microgravity, without gravity to pull the propellant through the transfer lines. There are several approaches to this problem. One is to use thrusters to spin both vehicles, creating artificial gravity through centrifugal force. The propellant will be pushed to the back of the tanks, and you can pump it through the transfer lines. But this requires precise coordination, significant propellant for the thrusters, and introduces mechanical stress on the docking mechanism. Another approach is to use surface tension. In microgravity, liquids form spheres or cling to surfaces due to surface tension. You can design the tank with internal structures that encourage propellant to flow toward the outlet using capillary action. This is how many satellite propulsion systems work, but it's slow, and it's unclear if it scales to the volumes needed for Starship. A third approach is active pumping, where you physically pump the propellant from one vehicle to the other, potentially using the receiving vehicle's acceleration to help settle propellant. SpaceX has tested small-scale propellant transfer during IFT-3, moving liquid oxygen between header tanks. But that was a few tons of propellant over a short distance. A full refueling operation would involve over 100 tons of propellant transferred between vehicles, and it needs to happen multiple times because a single tanker Starship can't carry enough propellant to fully refuel a mission vehicle. Current estimates suggest it would take somewhere between 8 and 12 tanker flights to fully refuel a single Starship in orbit for a Moon or Mars mission. Each tanker launches, reaches orbit, rendezvous with the depot or mission vehicle, transfers its propellant, deorbits, and lands. Then it's refurbished and launched again. This is why reusability is so critical. If the tankers were expendable, the cost would be prohibitive. But if each tanker can fly dozens or hundreds of times, the cost per refueling operation drops dramatically. SpaceX has publicly stated they intend to demonstrate orbital refueling within the next few years, probably by 2026 or 2027. They'll likely do this by launching 2 Starships, docking them in orbit, and transferring propellant between them while monitoring every aspect of the operation. It'll be one of the most complex on-orbit operations ever attempted. But it's essential because Starship's payload capacity to low Earth orbit is around 100 to 150 tons, depending on configuration. That's more than any other rocket, but it's not enough to send a meaningful payload to the Moon or Mars. The physics of the rocket equation are unforgiving. To reach the Moon, you need a delta V, a change in velocity of about 3 kilometers per second beyond what's required to reach low Earth orbit. To reach Mars, you need around 6 kilometers per second. Starship can't do that with a full payload and the propellant it launches with. But if you refuel it in orbit, suddenly those missions become possible. A fully fueled Starship in orbit has enough delta V to go to the Moon, land, and return to Earth, or to go to Mars, land, and potentially return if you can make propellant on Mars. This is the architecture. Launch the mission vehicle with payload but minimal propellant. Launch a series of tankers that fill it up in orbit, then send it on its way. It sounds complicated, and it is, but it's the only way to make the economics work with current technology. The alternative would be to build an even larger rocket, something beyond Starship's scale, and that would be even more expensive and complex. Another technology challenge is long-duration life support. If you're sending humans to Mars, the trip takes about 6 to 9 months each way, depending on the orbital alignment of Earth and Mars. That's a year and a half in space, plus however long you stay on Mars, which for propellant production reasons is likely around 18 months. So you're looking at a total mission duration of about 3 years. Keeping humans alive in space for that long is hard. You need to provide oxygen, remove carbon dioxide, manage humidity, recycle water, handle waste, provide food, and protect against radiation. The International Space Station does all of this, but it's the size of a football field and required decades of development. Starship has to do it in a much smaller volume and without regular resupply missions. The Environmental Control and Life Support System, ECLSS, is one of the most critical subsystems for crewed Mars missions. SpaceX has been relatively quiet about the details, but we know they're working on it. The basic requirements are well understood. You need a carbon dioxide removal system, probably using zeolite beds or a similar technology that absorbs carbon dioxide and can be regenerated. You need an oxygen generation system, probably electrolysis of water to split it into oxygen and hydrogen. You need water recycling, capturing moisture from the air, processing wastewater, and purifying it for consumption. The ISS recycles about 93% of water, and Starship will need similar or better efficiency. Then there's food. For a 3-year mission with, say, a crew of 12, you're looking at around 40 tons of food if you don't grow any on board. That's a significant fraction of your payload capacity. Growing food in space is possible. Astronauts have grown lettuce and other crops on the ISS, but scaling that up to feed a crew for 3 years is a major challenge. Most Mars mission architectures assume you'll bring shelf-stable food and possibly grow some fresh vegetables to supplement. Radiation is another massive problem. On Earth, we're protected from cosmic radiation by the atmosphere and the magnetic field. In space, you're exposed to galactic cosmic rays and solar particle events, high-energy radiation that can damage cells, increase cancer risk, and cause acute radiation sickness during major solar storms. The ISS is partially protected by Earth's magnetic field, since it orbits at low altitude. Mars has no magnetic field, and the trip to Mars takes you far beyond Earth's protection. Shielding against radiation is difficult, because the most effective shielding is mass. Thick layers of water, polyethylene, or other hydrogen-rich materials can block or slow down radiation. But mass is expensive to launch. Every ton of shielding is a ton of payload you can't carry. Some architectures propose using the propellant tanks as shielding. If you position the crew quarters behind the tanks, the liquid methane and liquid oxygen provide some protection. But during the coast phase, when the tanks are mostly empty, that protection is minimal. Another approach is to accept the radiation dose and mitigate the health effects with medical treatment and monitoring. Astronauts on a Mars mission will receive significantly more radiation than any human has been exposed to before, possibly several times the career limit for ISS astronauts. The long-term health effects are uncertain. This is one reason why Mars missions are likely to use relatively young, healthy individuals and why mission durations are kept as short as possible. But despite all these challenges, the technology is within reach. It's hard, but it's not impossible. The bigger challenge is cost, and this is where Starship's reusability and low operational cost matter. If each Mars mission requires 12 tanker flights plus the mission vehicle, and each flight costs optimistically $10 million, that's $130 million per mission just for launch costs. Add in vehicle production, life support systems, payload, and operations, and you're probably looking at several $billion per mission. That's expensive, but it's not Apollo expensive. The Apollo program cost around $280 billion in today's dollars. A single Mars mission using Starship might cost $5 to $10 billion. That's within the realm of feasibility for a government space agency, or even a well-funded private effort. And if Starship flies frequently and costs continue to drop, those numbers improve. Now, let's talk about the mechanics of landing on Mars, because it's different from landing on Earth or the Moon. The Moon has no atmosphere, so landing is purely propulsive. You fire your engines and slow down. Simple in concept, though challenging in execution. Earth has a thick atmosphere, so you can use aerodynamic drag to slow down, which is what Starship does during re-entry. Mars is in between. It has an atmosphere, but it's thin, only about 1% the density of Earth's atmosphere. This is thick enough to generate significant heating during re-entry, so you need a heat shield. But it's too thin to slow you down enough for a safe landing using aerodynamics alone. You need engines, but the engines can't start too high because the thin atmosphere doesn't provide enough back pressure for efficient combustion. So, you have to fall through the atmosphere with the heat shield, slowing down as much as possible, then start the engines at relatively low altitude for a powered landing. This is called supersonic retropropulsion. firing engines while still traveling faster than the speed of sound. It's incredibly difficult because the exhaust plume from the engines interacts with the supersonic airflow in complex and unpredictable ways. The plume can create shock waves, destabilize the vehicle, and even push back against the engines, reducing their effectiveness. SpaceX has experience with supersonic retropropulsion from landing Falcon 9 boosters on Earth, but Mars is different. The atmospheric density is different, the speed is different, the engine performance is different. They'll need to test this, and the only way to truly test it is to send a Starship to Mars and try to land it, which they plan to do, potentially as early as 2026, during the next Mars launch window. These early missions would be uncrewed cargo flights, delivering equipment and supplies for future crewed missions. They'd also serve as tests of the entry, descent, and landing system. If the first one crashes, that's okay, it's a test. They'll learn from it and try again 2 years later during the next launch window. This is the same iterative approach they've used for Starship development on Earth. The difference is that the iteration cycle is 2 years instead of a few months, because of the orbital mechanics of Earth and Mars. Another critical technology for Mars is in situ resource utilization, ISRU, making propellant on Mars. The Martian atmosphere is 95% carbon dioxide, and there's water ice in the soil. If you can extract the water and combine it with carbon dioxide in a chemical reactor, you can produce methane and oxygen through the Sabatier reaction. This is well understood chemistry. It's been demonstrated in laboratories on Earth, but doing it on Mars at the scale needed to refuel a Starship is a major engineering challenge. You need to land mining equipment to extract water from the soil. You need power, probably from solar panels or a small nuclear reactor, to run the extraction and chemical processing. You need storage tanks for the produced methane and oxygen. You need to liquefy the propellants, which requires refrigeration. And you need to do all of this autonomously or with minimal human intervention, because the first ISRU systems will probably be deployed before crewed missions arrive. SpaceX has said relatively little about their ISRU plans, but it's safe to assume they're working on it, because without ISRU, Mars missions are one-way trips. You can land on Mars with the propellant you bring from Earth, but you can't launch back without refueling on Mars. The amount of propellant needed to launch from Mars, fly back to Earth, and land is far more than a Starship can carry from Earth to Mars. Even with orbital refueling before leaving Earth orbit, you'd use most of that propellant getting to Mars and landing. You'd have nothing left for the return. So ISRU isn't optional, it's essential. The first few cargo missions will likely focus on delivering the ISRU equipment and getting it operational. By the time the first crewed mission arrives, there should be propellant waiting for them. In theory, if it works. If it doesn't, well, that's why you test with cargo missions first. The stainless steel construction of Starship also plays a role in the Mars architecture. Steel is durable and relatively easy to repair with basic tools and welding equipment. If a Starship is damaged during landing on Mars, it might be possible to repair it using materials and tools brought on the mission or produced locally. This is important for long-term Mars operations. If you're building a permanent base, you want infrastructure that can be maintained and repaired, not delicate systems that fail if a single component breaks. Starship's robust, almost crude construction is well suited to this. It's a tool, not a precision instrument. Another aspect of Starship's design that's often overlooked is its volume. The payload bay is over 1,000 cubic meters. For comparison, The ISS's pressurized volume is about 916 cubic meters. A single Starship has more internal volume than the entire International Space Station. This volume is critical for Mars missions because you're not just carrying cargo, you're carrying life support equipment, scientific instruments, spare parts, food, water, and everything else needed for a multi-year mission. You also need living space for the crew. Spending 18 months in a cramped capsule would be psychologically and physically devastating. Starship's size allows for relatively spacious crew quarters, exercise equipment, research labs, and common areas. It's still not comfortable by Earth standards. You're living in a metal cylinder in space, but it's vastly better than previous crewed spacecraft. The interior layout of a crewed Starship hasn't been publicly detailed, but concepts show multiple decks connected by ladders or elevators, with crew quarters, a galley, a medical bay, and storage areas. During the coast to Mars, when there's no gravity, the orientation doesn't matter, but during powered flight and on the surface, there will be a clear up and down, and the interior is designed to accommodate both modes. SpaceX's long-term vision involves not just single missions to Mars, but a sustained campaign of flights, building up infrastructure and population over time. Each launch window, which occurs approximately every 26 months, would see multiple Starships depart for Mars. Some would be cargo flights, others crewed. Over decades, this could result in a permanent settlement with thousands of people. This sounds like science fiction, and maybe it is, but Starship makes it technically feasible in a way that no previous system has. The economics and logistics are still daunting, but the transportation system exists, or will soon. And transportation has always been the bottleneck for space exploration. The future of Starship extends far beyond just reaching orbit or even landing on the Moon. SpaceX's long-term vision is nothing short of making humanity a multi-planetary species, and Starship is the vehicle designed to make that happen. But even before we get to Mars colonies and interplanetary civilization, there are nearer-term applications that could fundamentally change how we use space. Let's start with Starlink. SpaceX's satellite internet constellation currently consists of over 5,000 satellites in low Earth orbit, making it the largest satellite constellation ever deployed. These satellites provide internet coverage to remote areas, ships at sea, aircraft, and anywhere else that traditional internet infrastructure doesn't reach. The current generation of Starlink satellites, called version 2 Mini, weigh about 800 kilograms each. They're launched on Falcon 9 rockets, which can carry about 21 of them per flight. Now, SpaceX is developing Starlink version 3 satellites, which will be much larger and more capable, potentially weighing several tons each. These satellites are too big to fit inside the Falcon 9's payload fairing. They're designed specifically to be launched by Starship. A single Starship could potentially launch over 100 of these larger satellites in one flight, or perhaps fewer, but much heavier ones. The larger satellites can have bigger antennas, more powerful transmitters, and greater bandwidth capacity. This means better service, lower latency, and the ability to serve more customers. But more importantly, it changes the economics. If you can launch 100 satellites at once instead of 21, and if the launch costs less because Starship is fully reusable, the cost per satellite deployed drops dramatically. This allows SpaceX to scale up the constellation faster and cheaper than competitors. It also gives them a massive competitive advantage in the satellite internet market. OneWeb, Amazon's Project Kuiper, and other competitors are all trying to build similar constellations, but they don't have Starship. They're launching on Falcon 9, Ariane 6, or other rockets that are more expensive and less capable. By the time they've deployed a few thousand satellites, SpaceX could have tens of thousands of larger, more capable ones. This isn't just about internet service. A massive satellite constellation has implications for Earth observation, climate monitoring, communications infrastructure, and even navigation. If SpaceX can deploy sensors or instruments on thousands of satellites, they can create a real-time monitoring network for the entire planet. Weather forecasting, disaster response, agricultural monitoring, tracking illegal fishing or deforestation, all of these become possible with ubiquitous satellite coverage. There are also more speculative applications. One idea that SpaceX has discussed is point-to-point transportation on Earth using Starship. The concept is simple. Instead of flying from New York to Shanghai on an airplane, which takes about 15 hours, you board a Starship, launch into a suborbital trajectory, and land on the other side of the planet 30 to 40 minutes later. Technically, this is feasible. Starship has the thrust and fuel capacity to reach suborbital velocity, and the heat shield can handle re-entry from those speeds. The challenge is everything else. Where do you launch from? You can't launch from downtown Manhattan or central Shanghai. You need a launch site, probably offshore on a floating platform, and you need infrastructure to transport passengers to and from that platform. Then there's the passenger experience. Launching on a rocket involves several minutes of high G-forces, up to 3 or 4 times Earth's gravity. That's manageable for trained astronauts, but uncomfortable for the general public. There's also noise, vibration, and the psychological factor of sitting on top of a controlled explosion. Would people actually want to do this? Some would, certainly, but it's unclear if the market is large enough to justify the infrastructure costs. There's also the regulatory nightmare. Air traffic control for aircraft is complex enough. Imagine coordinating suborbital rockets flying over populated areas. What happens if there's an emergency and the rocket needs to abort? Where does it land? What if debris falls on a city? These aren't unsolvable problems, but they're significant barriers. SpaceX has done preliminary work on this concept, including simulations and discussions with regulatory agencies, but it's not clear if they're seriously pursuing it or if it's more of a long-term possibility. Elon Musk has mentioned it in presentations, usually as a side note, but there's no active development program as far as we know. A more realistic near-term application is space tourism. SpaceX has already flown private citizens to orbit on Crew Dragon, and they've announced plans for private Starship missions. The first private Starship flight is supposed to be the Dear Moon mission, funded by Japanese billionaire Yusaku Maezawa, who has purchased an entire flight to take a group of artists around the moon. This mission was originally scheduled for 2023, then pushed to 2024, and is now targeting sometime after 2026, depending on when Starship is certified for crewed flight. The Dear Moon mission would be a free return trajectory, meaning the Starship would launch from Earth, fly around the far side of the Moon without entering lunar orbit, and return to Earth. The entire trip would take about a week. It's less complex than a lunar landing mission because you don't need to slow down to enter orbit or descend to the surface, but it's still a significant undertaking. The passengers would experience views of the moon that only 24 humans have ever seen, the Apollo astronauts, and they'd see Earth from a distance that almost no one has experienced. The psychological and philosophical impact of that perspective, often called the overview effect, is reportedly profound. Space tourism is often dismissed as frivolous, rich people paying to joyride in space, but it has practical implications. If you can make money flying tourists, that revenue can fund development of more capable systems. SpaceX is a for-profit company, and while Elon Musk talks about Mars colonization, the company still needs to generate revenue to survive. Starlink provides some of that revenue, but space tourism could provide more, especially if costs come down enough to expand the market beyond billionaires. Imagine a future where a trip to orbit costs $50,000 instead of $50 million. That opens the market to hundreds of thousands or even millions of people. You're not selling to billionaires anymore. You're selling to upper-middle-class individuals who save up for a once-in-a-lifetime experience. At that scale, space tourism becomes a significant industry, and the infrastructure built to support it can be used for other purposes. Another near-term application is satellite servicing and orbital infrastructure. Currently, when a satellite breaks or runs out of propellant, it's abandoned. It becomes space junk, contributing to the growing problem of orbital debris. But if you have a vehicle like Starship that can carry large payloads and crew to orbit, you could service satellites. Send up technicians with tools and spare parts. Rendezvous with a broken satellite, fix it, and send it back into operation. This extends the lifespan of expensive satellites and reduces the need to launch replacements. You could also use Starship to remove defunct satellites and other debris from orbit, cleaning up space and reducing collision risk. There are companies working on robotic debris removal systems, but having humans available to handle complex or unexpected situations could be valuable. Starship could also enable the construction of large structures in orbit. The International Space Station was built over more than a decade with dozens of launches. Each module was launched separately and assembled in orbit by astronauts. This was slow and expensive. With Starship, you could launch much larger modules, or even pre-assembled structures, and construct a space station in a fraction of the time. You could build orbital hotels, research facilities, manufacturing platforms, propellant depots, or even shipyards for constructing spacecraft that are too large to launch from Earth. This is the concept of an orbital economy, where significant industrial and commercial activity happens in space rather than on Earth. It's speculative, but it becomes much more plausible when launch costs drop by 2 or 3 orders of magnitude. If getting to orbit costs millions of dollars per ton, only the most valuable activities justify the expense. If it costs thousands or hundreds of dollars per ton, suddenly a lot more things become economically viable. Then there's asteroid mining. This is often dismissed as science fiction, but the economics are straightforward. Asteroids contain valuable materials, metals like iron, nickel, platinum, and rare earth elements. A single metallic asteroid could contain more platinum than has ever been mined on Earth. The challenge is getting to the asteroid, extracting the material, and bringing it back. All of this requires a lot of delta V, which means a lot of propellant, which means heavy launch vehicles. Starship, especially with orbital refueling, could enable missions to near-Earth asteroids. You'd send a Starship with mining equipment, robotic or crewed, rendezvous with the asteroid, extract material, and return to Earth or to an orbital processing facility. The economics depend heavily on the value of the extracted material and the cost of the mission, and right now, the numbers probably don't work. But if launch costs drop enough, and if automated mining technology improves, it could become viable. Even if you don't bring material back to Earth, asteroid resources could be used in space. Water ice from asteroids can be split into hydrogen and oxygen for rocket propellant. Metals can be used for construction. If you're building infrastructure in space, it's far more efficient to source materials from asteroids than to launch them from Earth's gravity well. This is the concept of space-based resource utilization, and it's essential for any long-term space economy. Now let's talk about Mars, because that's where this all leads. Elon Musk has been very public about his goal of establishing a self-sustaining city on Mars. He's talked about sending the first crewed missions in the late 2020s, landing cargo missions as early as 2026, and eventually building a settlement with 1 million people by the middle of the century. These timelines are almost certainly too optimistic. Space missions always take longer than initially planned, and Mars missions are among the most complex endeavors imaginable. But even if the timelines slip by a decade or two, the trajectory is clear. SpaceX is building Starship specifically to go to Mars, and they're making steady progress toward that goal. The first Mars missions will be cargo flights. These will deliver equipment for power generation, life support, propellant production, habitats, and rovers. The goal is to pre-position everything needed for a crewed mission before any humans depart Earth. This reduces risk and ensures that when astronauts arrive, they have the resources to survive and work. These cargo missions will also test the entry, descent, and landing system on Mars. As mentioned earlier, landing on Mars is different from landing on Earth or the Moon, and the only way to truly validate the system is to try it. If the first cargo Starship crashes, that's a setback, but it's not a disaster. You learn from it and try again during the next launch window. If the 10th Starship crashes, that's a bigger problem, but by then you'll have a lot of data about what works and what doesn't. SpaceX's iterative approach is well suited to this challenge. The first crewed mission will probably be a small crew, maybe 4 to 12 people, depending on how much confidence SpaceX and NASA, who will likely be involved, have in the systems. The crew will spend about 18 months on Mars, the minimum stay time dictated by orbital mechanics. During that time, they'll conduct scientific research, test life support and ISRU systems, and begin establishing infrastructure for future missions. The return trip will only be possible if the ISRU system successfully produces enough propellant to refuel the Starship. This is one of the highest risk aspects of the mission. If propellant production fails, the crew is stranded. There are backup options, like sending an additional Starship with propellant during the next launch window. But that's a 2-year wait, and keeping a crew alive on Mars for 4 years instead of 2 is much harder. So, ISRU has to work. SpaceX will undoubtedly test it extensively with the cargo missions before committing to a crewed flight. Assuming the first crewed mission succeeds, subsequent missions will scale up. More crew, more cargo, more infrastructure. Each mission builds on the previous one. Eventually, you transition from exploration missions to settlement. People start staying on Mars for multiple mission cycles, or even permanently. You establish permanent habitats, greenhouses for growing food, workshops for manufacturing, communications infrastructure, and eventually schools, hospitals, and all the other things you need for a functioning society. This is decades away, but it's the vision. A city on Mars with 1 million people, as Musk likes to say, sounds absurd. It probably is absurd, at least on the timelines he's mentioned. But even getting to 10,000 people on Mars would be an extraordinary achievement. It would represent a fundamental shift in humanity's relationship with space. We'd no longer be visitors. We'd be inhabitants. The justification for all of this, beyond the sheer ambition and adventure of it, is existential risk reduction. Musk frequently talks about making life multi-planetary as a form of insurance for humanity. If a catastrophic event, an asteroid impact, nuclear war, pandemic, climate collapse, artificial intelligence gone wrong, wipes out civilization on Earth, a self-sustaining settlement on Mars would ensure that humanity survives. This is a compelling argument, though it's worth noting that preventing catastrophes on Earth is probably easier and more cost-effective than building cities on Mars. But it's not an either-or proposition. We can do both. And there's something to be said for the symbolic and psychological value of expanding beyond Earth. It sends a message that humanity is not confined to one planet, that we have a future beyond our cradle. Critics of Mars colonization often point out the enormous challenges. Mars is a hostile environment. The atmosphere is too thin to breathe and doesn't provide meaningful protection from radiation. The average temperature is minus 63 degrees Celsius. There's no liquid water on the surface. Dust storms can engulf the entire planet. Growing food is difficult because the soil contains perchlorates, toxic chemicals that have to be removed. The gravity is only 38% of Earth's, and we don't know what long-term exposure to that level of gravity does to human health. We know that zero gravity is bad, causing bone loss, muscle atrophy, and cardiovascular problems. We know that 1G is fine, but 0.38 G is unknown territory. It's possible that it's sufficient to prevent the worst effects of microgravity, but we won't know until people live there for years. Then there's the psychological challenge. Mars is far away. Even at the closest approach, it takes light about 3 minutes to travel between Earth and Mars, which means a 6-minute round-trip communication delay. Real-time conversation is impossible. You can send emails or recorded messages, but everything is asynchronous. This sense of isolation could be psychologically difficult, especially for the first settlers who will be far from friends and family, with no possibility of returning quickly if something goes wrong. And there's the question of governance. Who's in charge on Mars? Is it a colony of Earth nations subject to their laws? Is it an independent entity with its own government? SpaceX is a private company, so are they in charge? Elon Musk has joked about Mars being a direct democracy where laws are easy to repeal, but it's unclear if he's serious or how such a system would work in practice. There are international treaties, like the Outer Space Treaty of 1967, that govern activities in space, but they were written in a very different era and don't address issues like private colonization or resource extraction in detail. These are complex legal and political questions that will need to be resolved, probably through negotiation and new treaties, as Mars settlement becomes a reality. Despite all these challenges, the technical capability to go to Mars is within reach. Starship provides the transportation. ISRU provides the propellant for return. Life support technology, while challenging, is understood. Power generation can be done with solar panels or nuclear reactors. Habitats can be built from materials brought from Earth or produced locally. It's hard, but it's not impossible. And if SpaceX continues to make progress at the rate they have been, the first crewed missions could happen in the early 2030s. That's only a few years away. close enough that people reading this might live to see it. The long-term vision extends even beyond Mars. Once you have a transportation system that can move large numbers of people and cargo between planets, the entire solar system becomes accessible. The asteroid belt, with its vast mineral resources, becomes economically viable. The moons of Jupiter and Saturn, some of which have subsurface oceans and might harbor life, become targets for exploration. Even more distant destinations like the Kuiper Belt or the Oort cloud, regions of the solar system filled with icy bodies, could be reached with sufficiently advanced propulsion systems. Some visionaries talk about interstellar travel, sending ships to other star systems. That's far beyond current technology. Even the nearest star, Proxima Centauri, is over 4 light-years away. At Starship's speed, it would take tens of thousands of years to get there. You'd need fundamentally new propulsion technology, something like nuclear fusion drives or antimatter engines, to make interstellar travel feasible. But Starship is the first step. You have to be able to move around your own solar system before you can think about going to another. SpaceX's influence extends beyond just the hardware they're building. They've fundamentally changed the culture of aerospace. Before SpaceX, the industry was slow, risk-averse, and dominated by a few large contractors with cozy relationships with government agencies. Innovation happened, but slowly. SpaceX showed that a small, aggressive company could compete with and eventually surpass the established players. They demonstrated that reusability was practical, that rapid iteration was effective, and that ambitious goals could be achieved on relatively modest budgets. This has inspired a new generation of space companies. Rocket Lab, Relativity, Firefly, and others are all following SpaceX's playbook to varying degrees. They're building reusable rockets, iterating quickly, and aiming to reduce costs. Even the traditional aerospace giants like Boeing and Lockheed Martin have been forced to adapt. United Launch Alliance, the joint venture between Boeing and Lockheed, developed the Vulcan rocket partly in response to SpaceX's competitive pressure. It's still not reusable, but it's more cost-effective than their previous rockets. The commercial space industry is now a real thing, not just a handful of enthusiasts, but a significant sector of the economy. Launch services, satellite operations, space tourism, and eventually in-space manufacturing and resource extraction are all becoming viable businesses. This creates jobs, drives technological development, and expands human capability. It also has geopolitical implications. The nation or group of nations that dominates space will have significant strategic advantages. This was understood during the Cold War, when the space race was as much about demonstrating technological and ideological superiority as it was about exploration. Today, the competition is less ideological but still real. China, the United States, Europe, India, and others are all investing in space capabilities, and the balance of power will partly be determined by who can access and utilize space most effectively. Starship, if it succeeds, gives the United States a significant lead, but that lead is not guaranteed. China is investing heavily and moving quickly. If SpaceX stumbles, or if regulatory or political challenges slow them down, others could catch up. There are people who oppose SpaceX and Starship on various grounds. Some environmentalists are concerned about the impact of frequent launches on the atmosphere and on wildlife near launch sites. Rocket exhaust contains water vapor, carbon dioxide, and, depending on the propellant, other compounds. At current launch rates, the environmental impact is negligible, but If SpaceX achieves their goal of launching Starships multiple times per day, that could change. There's also the issue of light pollution from satellite constellations like Starlink, which affects astronomical observations. Some astronomers have raised concerns that the thousands of satellites are interfering with ground-based telescopes, creating streaks in images and making certain types of observations more difficult. SpaceX has worked with the astronomy community to mitigate this, adding visors to satellites to reduce reflectivity and adjusting orbits, but it's an ongoing issue. Others oppose the concentration of power in private companies. SpaceX is enormously influential, and decisions made by Elon Musk and his team affect not just the company, but potentially the future of humanity's presence in space. Should one company or one person have that much influence? There's an argument for more democratic or international oversight of space activities, ensuring that the benefits are shared and that decisions are made transparently and accountably. These are legitimate concerns, and they'll need to be addressed as space becomes more accessible. But there are also the concerns of a successful endeavor. If Starship were a failure, no one would be worrying about too many launches or too much influence. The fact that these issues are being discussed is a sign that Starship is working and that its impact is being felt. As of early 2025, Starship has flown 6 times. The most recent flight, IFT-6, launched in November 2024 and successfully demonstrated the booster catch for the 2nd time. The upper stage also performed well, though SpaceX intentionally splashed it down in the Indian Ocean rather than attempting a landing. The next flights, IFT-7 and beyond, will continue to refine the system. SpaceX has said they plan to fly at least a dozen more test flights in 2025, ramping up to potentially 1 per month. Each flight will test new capabilities, higher re-entry velocities, different landing profiles, payload deployment, eventually leading to an orbital catch of the upper stage. That's the final piece of the puzzle. Right now, the booster is caught by the tower, but the upper stage still splashes down. For full reusability, the upper stage has to return to the launch site and be caught as well. SpaceX has said this will happen probably in 2026. Once that's demonstrated, Starship will be fully operational. They'll begin flying commercial missions, deploying Starlink satellites, launching payloads for other customers, potentially flying NASA cargo to the Lunar Gateway Station. Crewed flights will follow, probably starting with private missions like Dear Moon, then progressing to NASA missions for Artemis and eventually Mars. The timeline is uncertain, as timelines always are, but the trajectory is clear. We're living through a moment of transition. For 60 years, space access has been expensive, risky, and limited to governments and a few corporations. That's changing. Starship, if it succeeds, will make space cheap, relatively safe, and accessible to a much broader range of actors. What happens after that is difficult to predict. New industries will emerge. New possibilities will open up. Humans will go to places we've only imagined. And maybe, just maybe, we'll become a multi-planetary species. That's the vision. That's what the world's most advanced rocket is designed to achieve.